Okay, so now let's try to understand Simon's algorithm in a very different way, in a much more physical way. So in terms of something we talked about in the very first lecture, which was the double slit experiment. So remember the double slit experiment, we had a source of light, a screen with a slit in it, another screen with two slits, a backdrop where we had a detector, and when we had both slits open, even though the light was turned down so that it was being emitted as single photons, we got this interference pattern which the intensity of light that was hitting, the probability that the photon ended up at point X was given by this interference pattern. Okay, so let me argue that you can view Simon's algorithm as a sophisticated kind of double slit experiment, as a kind of interference experiment. So, okay, let's say that we have n qubits, we do Hadamard transform, and then we do another Hadamard transform. So, and let's say that instead of starting off in this state, all of them in the state 0, let's say that we start in the state in some particular state like u1, u2, 3un. So we have an n bit string u1, u2, 3un. U equal to u1, 3un. So now, what's the superposition in the middle here? What does this middle superposition look like? Well, remember in the middle we are in a superposition over all the n bit strings. So we are in a superposition over all n bit strings x, where each n bit string x has amplitude plus or minus 1 over 2 to the n over 2. And whether it's in the plus or whether the phase is plus or minus depends upon u dot x. Right? u1 x1 plus u2 x2 plus so on. Okay. Now what happens when you do another Hadamard transform here? Well, what happens is that your new Hadamard transform transforms this into summation over y, beta y, y. And what's beta sub y? Okay, so let's compute beta sub y. Beta sub y is going to be sum over all x of the amplitude of x, which is minus 1 to the u dot x over 2 to the n over 2, times the amplitude of going from x to y when you do a Hadamard transform. Okay, what's the amplitude with which you go from x to y? It's minus 1 to the x dot y over 2 to the n over 2. So now there are two cases. Case 1, y is equal to u. If y is equal to u, then this is equal to that, and so then beta y is just a summation over x of these minus ones. These two are exactly equal, so they square and go away, and you get 1 over 2 to the n. They're exactly 2 to the n x's, so you get 1. So it's completely constructive interference. All the 2 to the n contributions line up, and they all give value plus 1. Case 2 is y is not equal to u. In the case y is not equal to u, you should convince yourself that for exactly half the values of x, these two signs are equal, and for exactly half the values of x, these two signs are unequal. So you get +1 half the time, -1 half the time. So beta sub y ends up, these two, half these values cancel with the other half, and you get beta sub y equal to 0. So you get completely destructive interference. Right? So this is as though you had 2 to the n virtual slits. And as your light goes through these 2 to the n virtual slits, then this Hadamard transform makes them refocus. And what happens? Well, you get completely constructive interference at y equal to u and destructive interference everywhere else. Of course, you can see this by just observing that the Hadamard transform is its own inverse, and so if you start from u, you apply the Hadamard twice, you get back u. Okay, so what does this have to do with Simon's algorithm? Well, what we'd like to do is we'd like to somehow change the slit pattern in the middle so that the pattern of slits in the middle is determined by the input to the problem that we are trying to solve. And then we are going to see where the constructive interference happens, and that's going to give us the answer to the problem. Okay, so remember what Simon's problem is. You're given a 2-to-1 function f where there's a secret string s such that f of x equal to f of x plus s. So now what do we do? Well, remember the Simon's algorithm looks like this. You have these 2 Hadamard transforms, which is very much like what we were doing in our previous slide. But then in the middle we put in this quantum circuit for computing f. And what does this quantum circuit for computing f do? Remember, okay, so at this point we had a superposition over all x, n-bit strings of x. Right? At this point, what we do is imagine just moving this measurement on these qubits back here. So what do we end up with? Well, we measure these qubits, and now the first n qubits are in some superposition 1 over square root 2r plus 1 over square root 2r plus s. Right? So it's as though out of the 2 to the n virtual slits, we've picked out exactly 2 of them. Which 2? Well, each of them by themselves looks random, but they are related to each other in this very special way that they differ by exactly s. So what we've done is we've picked out 2 random slits, 2 slits which are randomly positioned among these exponentially many, but they differ by exactly s. And now when we look at the interference pattern, the interference pattern is interesting. There's constructive interference on exactly half of the 2 to the n bit strings, and completely destructive interference on the other half. But so when we do our measurement, we see a random one of these 2 to the n minus 1 strings on which there's constructive interference. But the interesting thing that we said is that if we sample any one of them, so if y is a string where there's constructive interference, then it satisfies this condition that y dot s is 0. And this gives us a linear equation that s must satisfy. Okay, so you can see Simon's algorithm as this very interesting double slit experiment. Okay, the slits are virtual, and they reflect the input to the problem that we are trying to solve. And then when we look at the output, we look at where, when we do a measurement, we pick out one of the strings at which there's constructive interference, and a random such string. But that random string yields a linear equation which gives us a constraint on the secret string S that we are trying to find. Okay, and these linear equations allow us to reconstruct S.